Okay, good morning. Today is a continuation of the fast multiple method lecture, but I'm going to introduce the fast multiple in the form of a matrix. So it's the same concept, but this is what happens when you view fast multiple method as a matrix operation. So say that you have like a geometry of 10 by 10 by 10 mesh, like you have a finite difference method. And then what the fast multiple method is doing is it's actually creating A inverse function and doing a matrix vector multiplication against the A inverse. So the original finite difference or finite element method will give you a sparse A matrix, and you will do AX equals B to determine the unknown X, and what you will get is an unknown. Well, let's call it U for this sake. And you can also just, if you can invert the matrix A and multiply it to the right-hand side B, you will directly get the unknown without iterating. And what the Green's function solution using the integral equation is doing analytically is doing exactly this. So if you turn U equals G times F, which is the equation that we've been calculating. If you remember, we were summing a G matrix from point I and point J against some number Q. So you can think of this as the right-hand side F. And this was giving you some answer U. And so what you were actually doing was you were solving this PDE by using an integral form and doing dense matrix multiplication. The reason why people don't usually do such a thing is because if you think of this A inverse, it's a dense matrix the same size as the sparse matrix A that you're trying to solve. So usually you have a big sparse matrix, but it's sparse, so you can solve it without too much problem. But if you do it this way without thinking too much, then you're creating a dense matrix A inverse the same size as your sparse matrix, and then trying to do a matrix vector multiplication on that. So doing that directly is obviously not a very efficient thing to do. But the fast multiple method is not doing the G dense G. It's doing more like a hierarchically sparsified G. So the diagonal blocks of the matrix G are solved in the fast multiple method directly. If you remember this picture here, the P2P part is solved directly. What that's equivalent to doing is the diagonal blocks and maybe the blocks next to them for the neighbors will be solved directly using a dense matrix. But then as soon as you move to the ones that are slightly far away, so these ones that are far away in the geometry in this picture are actually on the off diagonals, so far away from the diagonal, because the diagonal is the close ones. So you can think of the distance from the diagonal as the distance from what you're calculating. So it doesn't map one-to-one because this is a 3D proximity and this is more like a 1D proximity. So the mapping between a 3D proximity and 1D proximity is what needs to be done very carefully. But we use a space filling curve for that, and that's why we use the Morton index. But you can think of roughly as this distance from the diagonal as the distance in this geometry. And in that case, the analogy of these far big points here are these far big boxes in these areas here. So now you can see FMM that have this shape like this one in the form of a matrix vector multiplication that has a matrix with dense diagonal blocks and very hierarchically sparsified off diagonal blocks. And what I'm showing in this green picture here is the rank of these off diagonal blocks. So a rank of a matrix is, it's information content. And so if you have a big matrix that's dense, you can still have a small rank, like maybe 2 or 3. And in that case, if you apply SVD, singular value decomposition, then you can reduce this big dense matrix into a very narrow, like a tall and skinny matrix and a short and fat matrix like this, times a very small matrix. So you can represent this big dense matrix, so say that this was completely dense and full of numbers. You can represent this with very few numbers, and if you do this multiplication of this times this times this, it will reproduce the big dense matrix. But it's sort of a compression scheme by using just the singular values that are large to sort of compress in a lossy way, but still with controllable accuracy. You can compress any dense matrix to its its numerical rank that is accurate enough. So by using this kind of low rank approximation, the FMM is actually analytically forming this low rank approximation. So think of what this M and L was in now corresponding to this picture. You have, let's call this vector, or it's not a vector, it's like a tall and skinny matrix. This width is not 1, it's actually some small number. And let's call this one U, and this very small block B, and this long block V. Okay, so these U, B, and V things, if you think of what they are in this equation, is that this M is actually this V, and what translates, so this part here, the nabla n plus k times G thing, this thing is this B, and then what you multiply here is the U. So by multiplying these things, you can see that you get the original matrix G, but this truncation number P is now how much you can reduce this B to. So the size of this small block P can be like 2 or 3 or 4, and in our example we're using 1, so what we're actually doing in all the step 1 through step 8 that we did in the coding sessions is actually creating a 1 by 1, like a scalar value here, and then this long vector of 1s, we created a lot of 1s, and then we created another lot of U prime things here. Those were actually these things here. So what we were actually doing is now very clear. We had an analytical equation that calculates the equivalent answer to the singular value decomposition. So without doing any numerical linear algebra like singular value decomposition, which takes a long time, we can directly calculate the content. So every time we do something here, this operation, we get a value without doing any numerical linear algebra. We get the answer of U, B, and V directly. So now you see the correspondence between what we've been doing with the fast multiple method, both in terms of the mathematics and also in terms of the picture, the geometry, what it looks like as a matrix, what it looks like in the geometry, and what this multiple expansion and local expansion meant if you were to do it as a matrix. So there's a one-to-one correspondence. Now, there are a few questions we could ask. So if you can do it analytically without creating a matrix, then why do people want to create or study such thing as a H matrix? The answer is for us to be able to expand G, there were a few conditions. So first, we need to know G, right? Because if we don't know G, we can't calculate this thing here, the gradient of G. So we have to know what function is like an analytical form of the A inverse. You can't always do this. So for example, if you're calculating a Laplace equation or Poisson equation, Helmholtz equation, or Stokes equation, then you know this Green's function solution. So now I reveal why I use the letter G. It's because this is called the Green's function. And this is like a Green's function matrix, which is explicit calculation of the A inverse, actually. So for PDEs that have a Green's function solution, you can do this operation directly. Okay, and there are some other kernels that are not necessarily Green's functions, like radial basis functions or some kernel functions that you want to use in machine learning. So those functions are also a function of the distance, so they have similar properties, and you can sum them like this. But they're not necessarily Green's functions of anything. But still, because you know the analytical form of those equations, you can use this expansion. And so you can still use the analytical way to form these, the compressed low-rank approximation of the off-diagonal blocks. And so this kind of analytical H matrix can be used only if you know the original, forward operator, let's say, of the matrix vector, if you know the matrix vector operator's constructor. So if you don't know that, then what you can do is say that you were handed like some matrix G, that the person who gave you this matrix didn't tell you how they made a matrix G. They just gave you a dense matrix. And you could still do this type of calculation, because you can do a SVD for any dense matrix. Any dense matrix you input, you can just calculate the SVD, and you'll get these, the actual compressed form. So the equivalent of what this was doing analytically, you will be able to do numerically, and you can still construct the same tree structure and have the same kind of interaction lists, and still calculate the equivalent, all the equivalent operations, and have an order n, and this is the important part, you can have an order n method to do this operation. So if you did a dense matrix calculation, then even for just the matrix vector multiplication, you'd have n square complexity to do, because you have n square entries in your dense matrix. And the storage would also be n square if you stored the whole thing. But this one only stores, the order n amount of elements, because basically you're storing proportional to the number of nodes in a tree, and you have n nodes in a tree. And so what you have is a low storage and low complexity way of calculating dense matrix operations. You can view it that way. If you don't know, even if you don't know what G is, you can still view this as an efficient way of compressing dense matrices. So that's more like a black box approach to the H matrix. You're given blindly a dense matrix, and then you have to examine if it's compressible. And you're allowed to reorder the elements of the matrix. So this is something you can do inside the H matrix. While you're doing this compression, you want to reorder the elements in a way that the off-diagonal block compresses well, and this small block becomes small enough. If you reorder it the wrong way, say that you did like a random perturbation of the rows or something, and tried to compress the same thing, applied SVD to this big block here, then it won't compress very well. So reordering is also an important issue. In the same way that we had to do sorting when we constructed the tree. So there's sort of an analogy here as well. So the sorting that we did when we constructed the tree was actually the proper reordering to make this low rank approximation compress more on the off diagonals. That was what was happening geometrically here. So you can sort of map. It's good to know both sides of the matrix form and the FMM, the original geometric form, because you can map ideas back and forth, and you come up with many analogies. So the techniques that have been developed here, a lot of them are not used yet in this area. So there's still a lot that can be done, and I think one of the most significant ones is in the FMM community, when we do this translation operation for the M2L, this distance between x, why do I have this the notation is slightly different from what I've been showing earlier, but anyway, this is like the I prime and J prime distance vector. And if you look at the shape of this interaction list, some, if you have the same relative positioning, so say that you had a different blue box over here, and you were looking at the same relative positioning of the red box. There's always some red box that's in the same distance and same angle as this relation that you have here. So for those ones, this x vector is identical, and so this part, this matrix is identical. And so you have many, many duplicate entries. If you think of the analytical form, it's very easy to see if the vector x, if the relative positioning of the two boxes that you're calculating for the M2L are the same, and you have so many of these inside the whole domain. You have many of these that are just, like translations, but same relative positioning of the two red and blue boxes. All of these, this block B is identical. So you don't have to store all of these copies of the same blocks. And when you look at a matrix that's so big like this one, you can get away by just storing one copy. It's like this one is a lossless compression, say, in memory, because it's just not storing all the redundant information. And in the FMM, there is a way to retrieve, the appropriate copy of the matrix whenever it's necessary. So it's like not storing, but still accessible when it's necessary. So those types of schemes where you can retrieve those, copies without duplicating them everywhere is sort of something that's not used so much yet in this community. For example, that's one idea that can come from people who have implemented this one for a long time, that are sort of looking at this from the FMM point of view. So that's sort of all the analogies. Because I'm showing the two in one figure, it was good to explain everything when I'm showing this slide. Okay, yep. Yes.
So I think the reorder is important. But if I just get a matrix without knowing too much of that, because here we have a geometric view.
Yes.
So we sort of know which should go near us, which should go far.
Mm-hmm.
But if I just have an algebraic matrix, how do I know what is the right reorder?
I think in general, if you just had numbers, you wouldn't be able to just figure out from the numbers. Yeah. You would need some kind of information. Maybe so. Instead, if you were not given the dense matrix, but if you were given, like A, the sparse version first, you can use something like what the algebraic multigrids use. So algebraic multigrid is also it's like a black box way of figuring out the connectivity between the elements. So they just look at the numbers, but they're handed like the sparse matrix, and they look at the sort of connectivity between the elements, and then they do the grouping based on this connectivity. So it's like sort of figuring out the geometry from the matrix in that sense. So they can do it that way. But if you were just handed the dense matrix with a lot of numbers, then there's no way to even figure out, because it's the fully connected part that you're being handed. And in that case, you can't use the connectivity to figure out these things. So you need to ask the person who's giving you that matrix to give you a little bit more, I guess, for you to be able to reorder. Yeah. So if you were given both the sparse part and then the dense matrix corresponding, then you could do something algebraically. But yeah. So okay. But usually, so in the people who do H matrices, a lot of them are doing, so this kind of equation. They know where their dense matrix is coming from usually, and a lot of them, when they try to determine the admissibility, which is whether to subdivide or not the box, when they try to determine this admissibility, they actually get help from the geometry, underlying geometry. So ones that don't rely on geometry also exist, but you need to have some sort of connectivity information for that. So in conclusion, you need something else other than a dense matrix to figure out the ordering. Okay, so yeah.
Yeah, sorry, but this sparsity would based on the connectivity of a sparse matrix. Will that give us a good reorder? Because so it seems that the number doesn't affect how I reorder things. I just look at the connectivity, which means I just look at the sparsity.
Right. So yes, if you're talking about the case where you're just handed the sparse matrix and your objective was to solve, then the typical thing to do is to first minimize the fill-in, by the reorder. So your reordering objective would be to minimize the fill-in, but then you get the Schur complements that are dense, right? So then that part you apply this, and then even for that case, the Schur complement is generated from underlying geometry that you are sort of somewhat aware in that case, because you can figure out from the original connectivity the sort of the underlying geometry of even the Schur complement. And then that case, you're handed sort of a dense Schur complement, but it's not the same as being blindly handed a big dense matrix. So yeah, in that case, you can do something about it algebraically. Yeah. Okay, so and also maybe since this slide contains the most information, so I'll stay on this slide for a long time. So since you've touched upon the subject of using this as a sparse solver or preconditioner, you can, so first do the reordering, like a multifrontal method, and then for the Schur complement, you try to apply the kind of reordering that minimizes the rank. And so minimizing the fill-in, which is looking at the connectivity, and minimizing the rank, which is sort of looking at the distance, is mostly the same, because if you look at this kind of geometry, the connectivity is dense. You have a lot of connectivity where it's near. So looking at the distance and looking at the connectivity are almost proportional. Like if you in 3D, what's connected are the near ones. So you're never connected in this kind of geometry to the far points. So if you want to minimize the rank, you want to minimize the maximize the distance, and if you want to minimize the fill-in, you want to minimize the connectivity, or so it's as long as the connectivity and distance are proportional to each other, it's okay. If you're if you're not looking at some kind of strange graph that's connected to far away more densely, then those two things are nearly equal. The problem is mapping from 3D connectivity or 3D proximity to a 1D proximity. So there's always a point. So if you map this using a space filling curve, which is the way of mapping 3D proximity to 1D proximity, because the proximity inside the space-filling curve, which is a 1D object, is supposed to represent the 3D proximity quite well. But there's always a point where the space-filling curve wraps around and comes back and becomes close in the 3D geometry. But since it traveled a long distance until it got there, in the 1D geometry of the space-filling curve, it's far. So whatever is close in the 1D is close in 3D, but not the other way around. There's always something that's close in 3D but far in the 1D. So there's always something that's close in 3D, which means it doesn't compress, that is far in the 1D geometry, which is in the off-diagonal. So there's always some part of the off-diagonal that won't compress very well, or that you need to subdivide more in that kind of case. So mapping as you go to higher and higher dimensions, you'll see more dense objects appear in the off diagonal. For that reason, it's because you can never map higher dimensions exactly to 1D. If you were somehow magically able to do that, you would be able to very cleanly make larger and larger boxes as you go to the off diagonal. It happens very well in 1D and somewhat better in 2D. But for that reason, using an improper admissibility condition will not give you low ranks in your off diagonals in higher dimensions. And if you're looking at very high dimension kernels, then that's it becomes terrible. Nothing compresses in the off diagonal. So yeah, all these issues arise from the fact that what's close in 3D can sometimes be far in the 1D space filling curve. So yeah, and there's no way to completely map those two. So okay, so this is somewhat repeat of what I've been saying in the first slide, but the HSS is the matrix form. So this is hierarchically semi-separable. So there are many terms here. So I won't go through all of them, but some people call the matrix form the H matrix or H square matrix or HSS or HBS, or there are many names for this hierarchically clustered low rank approximation of the dense matrix. But so if you want to know the difference, there are a few key differences. So FMM doesn't construct the matrix. It actually just uses equations it calculates. Well, you can think of it as a matrix-free operation where every time you construct the entry, you do the multiplication to the vector and you erase it from memory. So you do construct the matrix in the sense that you calculate the entries, but then you throw them away immediately. So you never hold the whole matrix in memory. You just hold them one element at a time. So it has low memory footprint. So you can handle potentially much bigger problems. And then it has higher arithmetic intensity. So if you're calculating on GPUs that prefer higher arithmetic intensity, then these will give you more flops, basically, because they'll be compute bound on your GPU. And then for the matrix version, it stores the matrix. It does very similar calculations, but then it stores the matrix. So if you have many right-hand sides or many vectors that you want to multiply the same matrix to, then this one will have to recalculate the entries every time you want to apply. So it would potentially be wasting a lot of computation. However, this one will just store the matrix. So if you want to just apply it many times, or even like do like a LU factorization or Cholesky, and save that factorized hierarchical form and just keep applying many times, then in that case, this is very useful. So you need to choose which one based on your objective. So if you're solving a scientific problem that requires just one factorization and then many applies, and I'm talking about like thousands, then this will become very fast. So yeah, then you have different types. When I say admissibility, you can think of it as how much you're subdividing the blocks. So this one divides more. It's called like standard or strong admissibility. And the weak admissibility means you're only dividing like once, and then you go down and immediately divide the diagonal only once, and then once. But this one, you divide, but you divide this off diagonal again and again. So it's more subdivisions in the off diagonal. But this is the part that allows you to sort of handle higher dimensions and still have low rank. So you'll have more boxes with low rank, and I'll discuss briefly about the balance between having more boxes and having higher ranks. And there is a optimal way of determining that. So there are more advanced techniques recently, that sort of nest the hierarchy so that even for higher dimension problems, you can have a faster scheme. So the naive one had very high ranks in the higher dimensions, like if you did a 3D problem. But now you can sort of nest the compression so that these parts that didn't compress, you're going to compress in a different way. Also, there were some, so the original FMM could only handle the matrix vector, the forward operator. But now you have something like the inverse FMM, where you can handle the inverse operation with the FMM form. So not like necessarily creating and storing a matrix. So it still has the low memory footprint feature, but it allows you to use it as a solver now that you can calculate the inverse. And so some of the limitations, like I mentioned, are you need to have numerically low rank of the off-diagonal blocks. Otherwise, if this is completely dense, then this is not a fast method at all. It's just partitioning a dense matrix for no good reason. Okay, and this one requires an analytical form. Like I mentioned in the previous slide, it